These are the notes on forces, vectors, and equilibrium, and are found in your book, chapters 2.6 to 2.8. So, first, let's start with a warm-up question. Mark all that apply. Which of the following are forces? A, gravity, B, weight, C, tension, D, friction, E, all of the above. Go ahead and pause the video and answer the question. Did you say E, all of the above? Because these are all forces. Gravity is the force between any two objects with mass. It's a force of attraction, so we usually think of this as big things like the Earth and the Moon or the Earth and the Sun, but it could also be two dust particles that are attracted to one another through the force of gravity, which is in fact how things like the planets and the stars initially formed. Weight is the force of an object's mass combined with the acceleration from gravity, and on Earth that's 9.8 meters per second squared. So when we say gravity is 9.8 meters per second squared, we actually mean that that's how fast gravity accelerates things as they fall on Earth. And weight is a downward force. Tension is a force along like a string or a rope or a chain that's being pulled. So if you're swinging at the park, you have a force of tension on the chains that are connecting the swing to the crossbar. If you're playing tug of war, you have a force of tension along the rope. And friction is a backwards force between two objects that generally slows things down, but you also need in order to get moving in the first place. So what is a force? A force is a push or pull on an object or between two objects. And the unit of force is the Newton. And we write that with a capital N because it's honorary after Sir Isaac Newton, who of course is the father of the Newton's three laws, which have to do with forces and motion. But what you're going to find is in physics we have these terms like the Newton, the watt, the joule, but they all go back to are the units that we know of mass, either kilograms or distance, meters, or time, seconds. So what a Newton actually is 1 Newton is the force needed to accelerate 1 kilogram by 1 meter per second squared. So a kilogram is a little more than 2 pounds, and if you were to accelerate that, speed it up by 1 meter per second each second, it would take 1 Newton of force. And in class I'll pass around a kilogram so you can sort of see what that actually means. And so 1 Newton, therefore, 1 Newton, and this little dotted triangle, if you've taken geometry, you know that that means therefore. Therefore, 1 Newton equals 1 kilogram times meters per second squared, or a kilogram meter per second squared is a Newton. So that's force. A vector is an arrow that shows the directions and magnitude or amount or strength of a force. So here I have two force vectors. The upper one is obviously more force than the lower one. They're both pulling in the same direction or pushing in the same direction, and that you could say is backwards, and we say backwards because we orient it based on how we read in English. And then you could also say to the left. That would work. If you had a compass, you could give actual directions, like if there were a compass written on the page. And then, all we know about this is that the lower one is about half what the upper one is. We don't know actual numbers. There's no like centimeter to force conversion where each centimeter is a Newton or anything like that. But if the upper arrow were 10 Newtons, we could say the lower arrow is about 5. If the upper one were 12 Newtons, the lower one would be about 6. We don't know exact amounts, though. So then, using that knowledge, we make what's called a force vector diagram, which is a diagram that shows all the forces acting on an object. So here we have a situation. This is a school bus speeding up, moving forward. And we're going to have 4 forces on this. So we're going to have a forward force, a backward force, an upward force, and a downward force. So that downward force is the force of the bus's weight. And weight, again, is the bus's mass times gravity. And again, when I say gravity, I'm talking about the acceleration from gravity. So it's mass times 9.8. And that's balanced by this upward force. Those have to be balanced or the bus would accelerate through the road, meaning like fall through, or it would be lifted up above the road. And so that is called, that has two words. You'll see it as the support force. You'll also see it as the normal force. So your book, I think, uses both. This force then is the friction force. And then this force is often called the thrust, or the, sometimes it's even just called the forward force, whatever that's from. In this case, it's from the engine on the bus. And we're going to make that force larger than our backwards force because the school bus is speeding up. And so that one needs to be greater than friction. Now, in fact, in physics, we don't care so much about the object. So while it's nice to have a cute little school bus, you can also simply have a dot and then have your vectors radiating out of that dot. So this would show the same situation of the school bus going forward. It doesn't matter if it's a school bus or an ant or a piece of salami thrown across the lunchroom. It's the same thing. So now we're going to look at net force. Net force is the addition or subtraction of all the forces on an object, or the sum of the forces. Sum meaning addition. One of the things you're going to see is that some of the forces, like friction, are negative forces. So if you add a negative, that's the same as subtracting. And so net force is when you've added and subtracted all the forces and you come up with one resulting force. If you remember back to when you did JA, if you did 8th grade in this district, you learned about gross income and net income, and gross was the amount you brought home. Or I'm sorry, gross was the amount you earned. Net was kind of what you brought home after all the taxes and things were subtracted out. So that's how that word net relates. You can see how it relates both to income and to force. So if we have our school bus here, and now I've put in some forces, and based on the magnitude of these forces, it's probably a little toy school bus. But we have a support force of 6 newtons, a weight of 6 newtons, a frictional force of 4 newtons, and a forward force of 10 newtons. So what do you think the net force is? Go ahead and pause this and see if you can figure it out. And you should have gotten that the net force on the bus is 6 newtons, because we have this 6 newtons is canceled by this one, and then we have a forward force of 10 and a backward force of 4, so you do 10 minus 4, and that equals 6. So that's how you get the net force of 6 newtons. And so when you're doing net force, occasionally you come across a situation where all the forces balance out, and that's called equilibrium. So equilibrium is when the forces are balanced, or the net force is 0. And you'll see the symbol of sigma. So this right here is the Greek letter sigma, and that generally in math means the sum. So this literally means the sum of the forces, F, equals 0. And that's when we're talking about equilibrium. So to look at what that would be, so here's our happy school bus again. And in this case, instead of having a forward force of 10 newtons, we have a forward force of 5 and a frictional force of 5, and so everything cancels out. You'll notice that the forward force and, say, the upward force, these two don't have to equal each other as long as they're canceled out by something. So these 5 newtons are canceled out, these are canceled out, and so we'd say this bus is at equilibrium. One thing that's important to note is that something at equilibrium could be stopped, which I think is what we think about, although if it were stopped, we would expect this situation where we don't even have a forward and backward force, but that the normal force and the weight force balance each other. This bus, though, could also be moving. You can be moving in equilibrium, and we'll talk about what that means a little later. But looking at your motion graphing, you should be able to see how moving at a constant speed often has some parallels to being stopped, to not moving at all. So you can kind of connect those ideas there and bring in your forces and your motion. One other thing you'll notice is so far we've only talked about forces that are parallel or perpendicular to the movement of the object. You could also have a situation like, say you have a teddy bear and you have some toddlers fighting over it, and you have one kid pulling with this amount of force and one kid pulling this direction with this amount of force and one kid pulling that direction with that amount of force, and you want to know what the net force would be. This is a little more complex, although more real to life. You don't always have situations where everything is parallel or perpendicular to the direction of travel. For this class, most of you will only be dealing with situations like the school bus. However, if you download level 3 for the forces and vectors, I'm going to teach you separately in class how you would figure out the net force for a situation like this. So that's something you may want to think about. Now is a good time to actually look at those 3 levels of forces and vectors and print the one you want for class tomorrow. And then also, if you have any questions, please make sure to put them in the comments section so that I can address them in class or respond to your comment. One thing to keep in mind is that when we're looking at force vector diagrams and you're looking at which level to choose, this is going to be more of a math-based thing than a reading-based thing. So make your decision appropriately that way.